Hello everyone, my name is Nurfatini binti Zahari and my metric number is 211069. I'm going to proceed to Hazim to introduce himself.
Hello, my name is Muhammad Hazim Haziq bin Lokman and my metric number is 213172.
Okay, hello everyone. My name is Tianlin and my metric number is 209467.
Alright, so for our topic, we are going to discuss about second order active low pass filter, our chosen topic. So in our introduction, a second order active low pass filter circuit is an electronic filter, typically compromising components such as amplifiers and capacitors. Designed for dynamic signal processing, this circuit allows low frequency signals to pass through, attenuating higher frequency. Next, we are going to look at key components. If Hazim can zoom in, if the viewers cannot see. So for the amplifiers, active components amplify the input signal. Uh, the capacitors essential for frequency-dependent signal filtering, and resistor, the last part is tune the circuit for specific frequency response. So the next part, Hazim will explain the circuit structure.
Okay, thank you, Fatini, for the explanation or introduction just now. So I would like to proceed with our circuit structure. So we have actually the first stage in our circuit, which is Vin enters non-feedback amplifier. So after that, we have the amplified signal passes through the C1, which is to blocking the DC that allowing the AC. So the second order active low pass filter circuit consists of two cascaded stages. So each incorporating of a non feedback amplifier and also capacitor. So the amplifiers are A1 and A2, as we can see here. Uh, Amplify the input signal, which is capacitor in C1 and C2, play a crucial role in filtering by allowing low frequency components to pass through the blocking the high frequency. So the next stage is the output of the first stage. So which is it is the signal that exhibits the to increase amplitude and pronounce the low frequency components. So in the first stage, the input signal undergoes amplification and filtering, resulting in a signal with increased amplitude and pronounced low frequency characteristic. So the output of the first stage then enter the second stage where the process is repeated. So in the second stage, the output at first stage enters non-feedback amplifier, which is A2. And also the signal will pass through the second capacitor, which is C2 in the circuit. So this cascading of stages enhance the filter's ability to attenuate the higher frequency and allows for a more refined control of the frequency response. So I think that's all.
All right, I will proceed to the next part is working principle. There is five important part that I will highlight. For the first part is frequency response. At low frequency, the capacitor's impedance is low, allowing signal to pass relatively easily. As frequency increases, the capacitor's impedance rises, leading to the filtering and suppressing of high frequency signals. Second, cut-off frequency. The cut-off frequency is where the filter starts to filter out signals. For a second order low pass filter, the cut-off frequency depends on the gain of the amplifiers and the values of the capacitors. It is typically defined as the frequency of which the filter reduces the input signal to 70% of its maximum value. For the third part is phase delay. Due to the phase characteristic of amplifiers, the filter introduces a phase delay, which must be considered in certain applications, especially in systems requiring a signal synchronization. The last part is amplification function. As the active filter contains amplifiers, the signal is amplified while passing through the filter, enhancing the output signal's amplitude. So overall, the second order active low pass filter circuit cleverly combines amplifiers and capacitors to achieve low pass filtering of the input signal. By adjusting the gain of the amplifiers and the values of the capacitors, the filter can be customized to meet the different applications. Then I will proceed to parameter selections for LPF circuit discussed by Ten. Telly, you can proceed.
Okay. Okay, so for my part is the parameters selection for LPF circuit Q values. The first is the definition of Q value. What is Q? Q is FC over 30F, where FC is center frequency and the delta F is bandwidth. So control of bandwidth. High Q is narrow bandwidth. But it's good selectivity. The low Q is wide bandwidth and gradual amplitude reduction. And next is amplitude response. High Q is stepper amplitude response near center frequency. Low Q is relatively flat amplitude response. And the phase response for high Q, it reduces small phase delay around the center frequency and critical for applications requiring a precise time domain response. Stability and distortion. Higher Q is benefits system stability and reduce distortion. Higher attenuation at frequencies outside passband. Selectivity and frequency response for high Q is beneficial for high selectivity applications, and for low Q is suitable for smooth frequency response. And next part is the cutoff frequency analysis. So we set up the frequency as 1 kHz and Q is equal to 0.707. The circuit type is second order unity gain Butterworth low pass filter. The transfer function coefficients is A0 equal to 1 and B1 equal to W2 CR1 multiply R2 multiply C1 and multiply C2. The transfer function is unity gain Salon key low pass filter. And the capacitor values C1 equal to 750 PF and C2 equal to 1.5 NF. And this part is the calculation of R1 and R2. The resistance values is R1 equal to 95.1 K and R2 equal to 203 K. And RC values of set of frequency, we set C1 equal to 750 PF. After calculation, we get C2 is bigger than 1.5 NF. Okay, and the next part is the low pass filter. As you can see, the oscilloscope, we got channel A and channel B. Channel A is 1.534 volt, and channel B is minus 1.038 volt. And we get the bolt plotter. As you can see, it reduced the magnitude. Okay, so that's the design or design low pass filter. Okay. And the next one.
Okay, thank you, Tianlin, for the explanation just now. So we proceed to why we choose this design and also the circuit. So actually, we have decided to choose this design, which is second order active low pass filter, is because of steep roll off function, which is it is provides a steeper roll off beyond the cutoff frequency compared to the first order filters and effectively attenuating higher frequencies. So we want to have higher frequencies in order to have a better signal. So the second one is we want to improve our selectivity, which is the second order filter offer better selectivity and allowing for more precise control over the desired frequency range while blocking unwanted high frequency signal. So this is to make sure that the signal that we're gonna have doesn't have a lot of interference into the signal. So the third one, we want to have this design is because to reduce phase shift. So compared to the higher order filters, the second order filters maintain a reasonable phase shift, making them suitable for application and also where the phase shift need to be minimized. So we want to have the phase shift as minimized as it can in order to have a better signal as well. So the last one, the reasoning, our main reason is the second order filter is a simple design circuit. So while more complex than first order filter, second order filters remain relatively straightforward to design and to implement the circuit. So it is striking a balance of between the complexity and also the performance. I think that's all from our group regarding the presentation for second order active low pass filter by group 10. That's all from me. Thank you.